Hello everybody, welcome to Introduction to Machine Learning. This is lecture 9. So in this video, we'll talk about classification problem in general. So essentially we're focusing on logistic regression model. What I'll cover in this video is the mathematical interpretation of logistic regression, the estimation part, different techniques that are used to estimate the model, and then finally we'll look at the Python implementation of logistic regression. The question that we're looking at, and this goes to the data set that I'm using. This is available on Kaggle. I'll share the link in the description. People on social media are exposed to a specific product. It could be anything. So this is done by a marketing company essentially, right? So given the age and income, can you find if a person will buy a product or not, right? This is an important question. And if you think about this question, this is more about whether a customer purchased an item or not. So we are not essentially looking at a number that we've been predicting until now, for example, in regression models. That's why this is a classification problem. To elaborate this further, let me draw a graph. And obviously this is not the perfect number graph, but this will give you an idea of what I mean. Let's say I have two predictor variables. One is age and the other is income. And the way I'm representing my outcome is whether a customer purchased the product or not. So purchase is going to be an O, and not purchase, let's represent that by an X, right? And let's say this is distributed something like this. And by the way, age is, for example, 18, 23, 28, 33, and so on. And then 50K, $50,000, 100, 150, 200, and so on, right? And this is people who purchased, not purchased, and so on, right? So let's say this is my data. This is how this looks like. And my goal is to find out whether somebody purchased this item or not. So as you can see, income is not really impacting the outcome. So we have like all income ranges in getting the output, whether it's purchased or not. But when we look at age, there is some kind of demarcation, maybe somewhere here. I'm not sure, but there is some demarcation there. Okay, so essentially we figure out by looking at the data that age is important according to this picture, right? Now, can we just segregate age from this entire data set and then maybe plot it again, right? So for example, age and then the outcome purchased or not purchased. So let's say not purchased is here and purchased is here, right? So not purchased is a 0, not purchased, and purchased is a 1, right? And when I try to plot age here, essentially what I'll get is some people of maybe lower age purchased, so they'll lie on this line, and then people who did not purchase will lie on this line, right? And if I try to fit a linear model just like we've done before, what I'll get is maybe a straight line, but as you can see, this does not really represent the outcome here. This does not really encompass what I'm trying to predict here, because some of the values are maybe concentrated here, the other ones are concentrated here. And this is not what a linear model can handle. And so in order to deal with problems like these, we have logistic regression, right? Okay, so I had another slide. I could have drawn it here, but I just jumbled up things there, but that's okay. Okay, so what is classification? It has qualitative response variables, just like in our example, we had, what was that? Purchased or not purchased, right? So that was our response variable. Qualitative response variables, the qualitative response variable y, so now I'm representing it with y. It can take a value from a set C. So for example, in our set C, it was purchased or not purchased. It could be an email being spam or ham, of a particular person survived or not, and so on, right? Given a feature vector, which in our case was age and income, right? So my X could be all my predictor variables. Okay, so this is how the classification problem is defined. Now our goal, our task, is to figure out a function which we called a classifier. It's nothing but a mathematical function that will take these feature vectors or this input as the entire data and then predict a value for y, which is my response variable, which is usually qualitative in nature. Right? So this is how a classification problem is built, and this is what our task is. And more specifically, we essentially estimate probabilities that X belong to a category in Y or not. What that means is whenever we are building a classifier, we are essentially trying to calculate or predict probability of whether this particular observation will lie in this class or that class, whether this particular customer will purchase or not purchase, right? For instance, finding the probability whether an email is spam or not, a customer purchases something or not, and so on. There are numerous examples, but this is what a classification problem looks like, and we are solving this classification problem using logistic regression. Now, going more into what logistic regression looks like, why we use it, right? So for any default classification problem, just remember that we are essentially trying to represent something like this: 0 if no, 1 if yes, right? Or then depending on whatever your question is. So essentially we're trying to predict probabilities of, for example, in our case, a person selected this item or not. Okay, so here, what is binary logistic regression? Why I'm calling it binary? Because we are focusing only on whether a person selected something or not, whether an email is spam or not. There could be more than one class for sure. Okay, so logistic regression or binary logistic regression is used for classification tasks. The outcome is a binary value. For example, a patient has a disease or not, spam or ham, pass or fail, and so on. And then here on the right, you can imagine, let's say in our problem, this is age and this is purchased or not. Right, you can see if we are trying to fit a linear model, as I said before, it could exceed 1 or be less than 0, right? And this will also be a little difficult to use a linear model when we have more than 3 categories of responses. For example, I could have 0, 1, 2, right? And if I'm trying to fit a linear model, it will take the order as something important. For example, if I have 3 classes that I encode as 1, 2, and 3, my linear model is going to take those as some possible outcomes, and it will take the order as important, which is not what we're looking at, right? We are simply trying to find out what observations lie in class 1, what observations lie in class 2, what observations lie in class 3, right? So for that, we have this logistic regression model. It's so look at the right-hand side. It looks something like this. It fits a sigmoid function to this data. So as you can see, it lies between 0 and 1. So it kind of restricts the outcome between 0 and 1. That's the most important part. And we look at its mathematical representation and why it is restricted within 0 and 1. But this kind of renders it this important property that we can deal with classification problems easily by using a sigmoid or this curve, essentially, right? Or more simply put, this logistic regression curves gives probability for the response variable. Okay, so the mathematical form of a logistic regression, or that curve that we just saw, essentially looks like this, right? For example, we said that age affected purchase more, right? So let's say X is age only, or it could be like more variables. So probability of X essentially here means the probability of getting how many Y's equal 1 given X. This is what this means here, right? And how many times we'll get that. And what is E? E is a mathematical constant. It's also called the Euler's constant. It has a value equal to 2.78. Okay, so that's how the logistic regression looks like. And as you can see from the equation itself, whatever values my parameters beta 0, beta 1, or x will take, p of x will always be between 0 and 1. Right? This is important. And again, reiterating, this is my feature vector, right? So these are the input variables. This is my feature vector. And these are the parameters that I'll try to estimate using my logistic regression model. Okay. Also, one transformation of linear model that ensures probability value is also called the log odds or logit transformation. I just wanted to show you, just in case, if I take a log on both sides of this equation, what I get is log P of X over 1 minus P of X equals beta 0 and beta 1x. What this illustrates is that this is also a linear model because you can see it's linear in parameters, right? So this is also a linear model, so that's why we sometimes call it a linear logistic regression. Now the question arises, how do we estimate these values? How do we estimate these parameters? Because remember, in the linear model, we were using the ordinary least squares. Essentially, we're getting the mean squared error and also using gradient descent. So there were various ways of getting these parameters. How do we do that in logistic regression? I'll talk about two of these methods. The first one is MLE, or the maximum likelihood estimation. The estimator somewhat looks like this. So let's say the estimator, obviously a function of model parameters. It looks like this. Multiply all the i's such that the outcome equals 1, all the probabilities for those observations that have outcome equals 1, and the probability 1 minus the probability for all the observations that have the value y equals 0, right? So this likelihood function actually gives the probability of observed zeros and ones in the data. So we pick beta 0 and beta 1 or other parameters to maximize the likelihood of observed data. Most available libraries in Python and even in R use this technique to estimate the model parameters in logistic regression models. However, we have another way of estimating these parameters, which is again using gradient descent. I'm not going too much into the details of that. Just a reminder, we used mean squared error like in linear regression. We could have done that here again, right, to determine the cost function. But the issue with logistic regression is that when we calculate the cost function using that technique, we do not get a convex function. Now, what does that mean? Remember the discussion around gradient descent, where we looked at a function like this. So this is convex and it had a single minimum value, right? So many local optimums might exist if the function is non-convex. So just like to simply put, you can have something like this, and gradient descent might converge to one of these points, and we might find the minimum here and miss out this point, which is actually the global minimum, which is why we cannot directly use mean squared error. What we do is we define our cost function something like this. So we define our cost function, and just to be consistent, this equation is showing you h. This h is nothing but our p, the probability value that we just saw in the previous slide, right? Just to make it consistent. So the cost function in terms of the probability values, and the dependent variable, which is y, is something like this. So minus log p of x if my y is 1, if the response variable is 1, for example, in our case, if the customer purchased something. Otherwise, it's minus log 1 minus px if y is 0. And as I said, I'm not going too much into the details of this, but then this can be rewritten in this form, this cost function. And this is what we'll try to minimize. So the objective function for the gradient descent becomes to minimize j of theta, which in our case is beta, right? We're representing all the parameters by beta, so just let's be consistent, right? So that's that. But essentially, we'll try to minimize that using gradient descent. Just like we talked about gradient descent in the previous videos, then it goes on in that order, right? So we talked about two techniques of getting the model parameters for logistic regression. Let's actually go and implement the model and see the outcome, right? So, okay, let me keep this and let's go here, right? So now I have the data from here. I've provided the link in the description. So this is from Kaggle. This is social network ads. And as you can see in the data, it has a lot of feature vectors here, feature variables or predictor variables. What I did was, as I've done before, I simplified it. I just got age and the salary for each person, and then the outcome, which is purchased or not. So I just simplified the data set, and here is the code. Now, a lot of it I'm not repeating because it's from the previous videos, importing the libraries, right? And then Importing the data set and creating the X and the Y. Again, we've looked at multiple times before. Splitting and feature scaling. If you're not sure how to do this, please look at the previous videos in this series. So here we got that. Now I'd like to talk a little bit about how we did this. How do we get, now we've been using linear regression until now. Notice I'm importing logistic regression instead of linear regression. If in case of other models, you're not sure how to arrive at the correct class from the scikit-learn library, I wanted to demonstrate that here. All you have to do is do a Google search on scikit-learn. You'll go to this link, scikit-learn machine learning library. And in that, let me just show you where it takes you here. And then directly go to this classification. Now notice you'll have all these models here. Just go to the classification part, and then you can see logistic regression, right? Directly go to APIs here. You can directly find the API that you're looking for a particular problem. So that's how I got this. So from scikit-learn.linear model, as I said before, this is a linear model. Import logistic regression, then create an instance of that. A random state equals 0 is optional. This kind of creates a seed that whenever I run this, it uses the same value. So that's essentially that. And then obviously you'll have to fit the train and the X train and the Y train to create the model, right? So let's run that here. Okay, so the model is created and you can see the different outcome values, which essentially do not make a lot of sense yet. They will make a sense when we do predict. We have again seen predict before with regression, but now notice the name of my instance is classifier. So I'm doing a classifier.predict, and then obviously I'll have to transform because I'm directly trying to find out if the person whose age is 30, right? Because this is how my data looked like, and whose salary is around, let's say 87,000, or maybe let me change it with some other value, right? So I'm trying to find out if somebody whose age is 35 and salary is maybe 100K, whether that person is going to purchase or not, right? So this is what we wanted to do. And a 0 tells me no, the person is not going to predict according to our model. Again, we have seen this before, right? So I just copied and pasted from the previous code for the multivariate regression that we did, essentially trying to print out the predicted and the actual Y's in the test set, right? So you can see here, for a lot of values, as you can see, the predicted and the actual values are correct, but for many of them are not, right? So what is a way of kind of evaluating for how many values in the test set did we get the correct values, right? For that, we use something called the confusion matrix. That will give us the exact evaluation of our result. The way to do that is use the scikit-learn matrix library, right? So again, I'll do sklearn.matrix, and the class that I'm going to import. In fact, let me import two classes. The first one is confusion underscore matrix, and the second one is accuracy score. So this gives us an overall accuracy on the test set, right? So how many did we predict correct? Okay, so then again, let's create an instance of the confusion matrix. The way to do that, confusion underscore matrix, right? That's the name, and it's on the test, y underscore test, compare it with the y underscore predict, right? So that's what I'm going to do now, and print C, right? This is giving me some accuracy score. Oh, okay. So it's giving me it's unused. Definitely we're going to use it. Let's use it here. Accuracy underscore score. And the way to use that is, again, what do we want to test our accuracy on? So that's y underscore test and y underscore predicted value. Okay, so this is going to tell us, this is the first step in evaluating our model, how good our model predicted is like this. Okay, so we get the confusion matrix, we get the accuracy score. How do we read this, right? So this is essentially telling us here that the correct prediction of class 0, people who did not buy anything, is 65. So we predicted them correctly. 65 who did not buy anything, our model is also saying yes, they did not buy anything. 3, however, are wrong for the class 0, right? Similarly, for class 1, our model predicted correctly that 24 people who actually bought something, our model also predicted, yes, they bought something, and 8 who did not buy anything, our model predicted that they did, right? And 0.89 or 0.89 is the accuracy score, as you can see. What it tells us that 89% of correct predictions are there in the training set. Okay, so this gives us an idea of logistic regression, the basics of logistic regression, and how to implement it in Python. Thank you.